So in this video I'm going to talk about the Cassini identity, about the Fibonacci numbers. So the Fibonacci numbers are defined recurrently, so as f1 is equal to 1, f2 is equal to also 1, and then fn plus 2 is equal to fn plus fn plus 1. So now we have this Cassini identity that says that the product of fn minus 1 and fn plus 1 minus fn squared is always equal to minus 1 to the power of n. So there are multiple ways to prove it, but I'm going to show how to prove it using matrices. So in one of the previous videos about the Fibonacci numbers, I already showed how matrices can be employed to prove various facts about the Fibonacci numbers. And in particular, I showed how to derive the formula for the Fibonacci numbers, like the general formula, not the recurrent one, but the general fn expressed in terms of n. And in particular, I showed there so this recurrent relation can be basically rewritten in the matrix form like this. So fn plus 1 fn, the vector, the vertical vector, is equal to this matrix 1 1 1 0 multiplied by the vector fn minus 1. And we can verify this directly. So when we multiply the vector, let's consider this multiplication. So when we multiply the first row by this column, we get that fn plus fn minus 1 should be equal to fn plus 1, right? So this is exactly this recurrent formula for one lower index. So fn plus 1 is equal to the sum of the two previous terms in the Fibonacci sequence. So fn and fn minus 1. So this is exactly what we get. And when we multiply the second row in this matrix by this column, we get that fn multiplied by fn multiplied by 1 plus fn minus 1 multiplied by 0, so 0. So in total, this product, the result would be like fn only. So fn multiplied by 1, and the second term goes to 0. So fn should be equal to the second term in this column, which is fn. So it holds. So now we can extend this slightly and write that not in terms of vectors, but in terms of matrices. So we add another column to this. So we write that the matrix fn plus 1 fn minus 1 is equal to the matrix 1 1 1 0 multiplied by the matrix Fn Fn minus 1, Fn minus 1, Fn minus 2. So basically the same matrix with the one lower index. So when we like to verify that this is true, well, you can just directly multiply two matrices. So like basically when we multiply this matrix by the first column, this is like exactly what we already verified, right, previously. So we would get we would get the first column here. And when we multiply it by the second column, we should get the second column here. And this is the same formula, just with the lower index. Yeah, so well, you can verify it in detail, but like you can believe me that this is so this matrix multiplication. So this formula for matrices it's just a direct corollary of the recurrent formula for the Fibonacci numbers. So now we like let's denote the like this matrix. Let's denote it by F capital M. So then this matrix would be Fn minus 1. So and this matrix let's denote it by A. So our formula is rewritten as Fn is equal to A Fn minus 1. And the matrix A is constant. It consists of 0 and 1. It doesn't depend on n. So basically this is the matrix version of the recurrent relation for the Fibonacci numbers. But from this we can conclude that like we can use the same recurrent formula to express f minus 1. So we write this is a multiplied by a f n minus 2, right? And so now we group together two a's and write that this is equal to a squared f n minus 2. And we continue, then we can express f n minus 2 using the same recurrent relation in terms of n minus 3 and so on. And finally we arrive that it would be equal to a to the power n minus 2 f2. And we can't lower further the index because how can we actually? no, we can't, because like in the matrix Fn there is the term Fn minus 1 with one lower index, and the smallest index for the Fibonacci number is 1, the way we defined it. Like, it's possible to define F0 as 0, but like that's not the way we defined it. So like we are going to use the smallest index F1, so the smallest index for the matrices is F2. Okay, so now we can express directly F2. So this will be a to the power n minus 2 so F2 so F2 basically is equal to F2 F3 F3 F1, right? And this is equal to n minus 2 2 1 1 1. And yeah, like yeah, it actually would be much more convenient to introduce F0. So like, well, one way to see it is just to observe directly that this matrix this matrix 2 1 1 1, so it's equal to the matrix 1 1 1 0 squared. So basically the same matrix as A. So basically A squared. This is equal to A squared. Like, you can verify directly that when we square this matrix we would get this, but another way to see it is to introduce F0. So when we introduce F0 equal to 0, we observe that it also satisfies the recurrent formula. So like F2 is equal to F1 plus F0. So this is equal to 1, this is equal to 1, and this is equal to 0. So this also satisfies the recurrent formula, and therefore we can introduce now the matrix F1, the matrix F1 as F2 F1 F1 F0, and then rewrite this as n to the power n minus 1 F1. So reduce the index one more, and then the F1, you notice, like, if we explicitly write it, what is F1? It's 1 1 1 0. So this is exactly matrix A. So this is A to the power n minus 1 multiplied by A. So this is a to the power n. And the same we would get, like without introduction of 0, we would get the same thing here. Like if we verify that this matrix squared would be this matrix, if you verify this directly, then again this is a squared, and again this would be equal to a to the power n minus 2 multiplied by a squared equal to a to the power of n. So in any case, like however we choose to derive it, we obtain the final formula that f so where we started all of this, so we started this chain of equality is fn. So fn so the final formula is that fn is equal to a, the matrix A to the power n. That is the final formula. So now we consider the determinant of the matrix Fn. So the determinant of the matrix Fn, so calculated directly, so the determinant is equal, so this is our matrix Fn. So the determinant is the product of the numbers on the main diagonal minus the product of the numbers on the other diagonal. So it's Fn plus 1 multiplied by Fn minus 1 minus Fn multiplied by Fn. Right? So now for convenience, like we rewrite the matrix here. Determinant of Fn plus 1, Fn minus 1, Fn. So it's equal to let's write it lower. So this is equal to Fn plus 1 multiplied by Fn minus 1 minus Fn squared. So this is the determinant, and observe that this is exactly the expression that is in the Cassini identity from which we need to prove. So the Cassini identity, right? So the expression in the expression on the left side is exactly the determinant of the matrix Fn. So we need to prove that this is equal to minus 1 raised to the power n. But on the other hand, so since we proved that the matrix Fn is equal to a to the power of n, from this we conclude that its determinant, so then the determinant, okay, let's write it here. So the determinant of Fn is equal to the determinant of the matrix A to the power of n, and this is actually equal to, because of the well-known property of determinants of matrices, this is equal to determinant of the matrix A raised to the power of n. And so now to calculate it, so the determinant of the matrix n can be calculated directly. So now we recall what the matrix A is. So we write it here. So determinant of the matrix 1, 1, 1, 0 of this raised to the power of n. And so the determinant is equal to 1 multiplied by 0 minus 1 multiplied by 1. So 1 multiplied by 0 minus 1 multiplied by 1. All of this raised to the power of n. So to simplify this expression, it's equal to minus 1 to the power of n, right? Because the first term, this is 0, and this is minus 1. Yeah, so the determinant, so we concluded that the determinant of the matrix a to the power of n, we calculated it directly, it's minus 1 raised to the power of n. This is equal to the determinant of f, not f to the power of n, but n is an index here, determinant of the matrix Fn. Yeah, so basically one way this determinant is equal to calculated one way, this determinant of the matrix Fn is equal to this expression, and calculated another way, this determinant is equal to minus 1 raised to the power of n. Therefore, we conclude that Fn plus 1, Fn minus 1 minus Fn squared is equal to the determinant of Fn, the matrix Fn, and this is equal to minus 1 minus 1 to the power of n. And this is exactly the Cassini identity that we needed to prove. That's it.